This is a series of three short videos where we will have a very short introduction to the calculation of the sample size and a little bit, just really a little bit of experiment design for especially for animal research, but it can be applied to anything where experimental design, statistical experimental design can be applied. So this will be the outline. So we will cover mostly sample size, but we will see a little bit concepts related to experimental design, and at the end we will give some references for those people interested in expanding all these ideas. So the sample size calculation refers to the famous N, so how many individual samples, animals you need per group, or if you have a single group in that group, to be able to show that the differences that you are seeing in your experiment are statistically significant. So let's say that you want to determine the differences between the mortality rate among different bacterial strains and treatments. So you will have multiple groups or a couple of groups, and then you will compare. One of the groups will be treated in one way, the other group will be treated in some other way, and if you don't do anything, the control group, you expect that 80% of the animals die from the infection, while if you have a successful treatment, then you expect that none of the animals die from the infection. And there is a gap between the two groups that you want to detect. So so far you haven't done the experiment, but this is the kind of gap that you want to detect with a statistical power of 90% and a confidence level of 95%. So when you do the experiment, if the treatment is partly successful, then the number of animals dying, let's say that drops from 80% to 40%, but with the number of animals you will have, you will not be able to show that that drop from 80 to 40% is not due to chance. So it could be compatible with there is no difference between the two groups. So the point is, how many animals do I need to put in each one of the groups, so that if there is a really big change, I am able to detect it. And using too many or too few animals is a loss of time, a loss of money, and it is unethical, because you are doing bad things to animals that at the end they are, if you use too many, it is clear that you could have used fewer, so the extra animals that you need is a loss of time, money, and it is unethical. But if you use too few, it is also unethical and a loss of time and money, because if you use too few, when you try to compare the two groups, the p-values will never be below this 5% threshold. So that means that you have done the experiment for nothing. So it is really unethical. So you must use what it takes. So in this example, where we want to go from 80 to 0, you just need 4 animals per group. So there is a technical detail, that is that 0% is not something that you can use in the calculation. So you what you mean actually is to have a very large drop. So we substitute 0 by 2%, so the gap is 78. So but apart from this technical detail, it is the point is that you don't need to use too many. So if you just want to see almost cure from the infection, then it takes only 4 animals, and there is no point in using 8 animals or 10 animals per group, simply because you have always worked with this, or there is no point in using fewer just to reduce the number of animals. So in these 3 R's, reduction doesn't mean reduction to the point of compromising the analysis of the results, because otherwise, if you compromise it, at the end you don't have anything to compare. So I like to think of this sample size problem in the following way. So there are 2 different trends. So one is that I'm expressing this in money, the cost in money, but it is just a general cost. So that is a part of the experiment that whose cost grows linearly with the sample size. So for instance, this one, the larger the sample size, the larger the cost, because you will have, if you double the number of animals, you will have double the cost to feed them, to maintain them, to it is double your time to apply all the treatments, to analyze all the data. So this part of the cost is clear. On the other side, there is another much more difficult to measure cost, that is this one. So this one is the cost associated to taking an incorrect decision. So if you have a lot of animals, this very difficult that you will take incorrect decisions. So you have so much evidence that the possibility of having a false positive or a false negative is really low. So because you have a lot of evidence in favor or against your treatment. But if you have very few animals, then it could happen that you have a false positive or a false negative. False positive is you think, for instance, that your treatment is effective when it is not, and because you were unlucky with your sample, and then because of that, you continue doing experiments with your treatment, and later you will discover that the treatment was not useful. So, but there is a lot of cost associated to the later experimentation. If you have a false negative, you think that your treatment is not effective, but actually it was, simply that you were unlucky with your samples. And again, your p-value when you did your first comparison was not below this 5% threshold, and then you thought that the treatment was not effective. But then there is a cost of opportunity. Maybe you could have developed a very good treatment with that compound, and simply because you were unlucky the first time you tried, you discard it. So the probability of having a false positive or false negative increases when the sample size is very low. So there is a cost that decreases not linearly, but it decreases with the sample size. And the total cost of your experiment is the addition of the two. So there is a region here around 20-25 where you have an optimum cost effective trade-off, and then beyond that, adding more animals, it is not adding much in terms of information, and removing animals, it has a high cost in terms of committing false positives or false negatives. And this region, I also like this figure because it reveals that the optimum number is a region, actually, because it is you are designing your experiment in a setup in which there is a lot of uncertainty. So there is no there are many variables or parameters that have to be estimated in advance. You may make mistakes. So this answer is not written in stone, so that it is not that the optimum is 23 and not 22 or not 24. So it is a region somewhere between 20-25, and what it shows is that it is not 8 and it is not 80. So that is an option, and these curves are different for each experiment, so they may shift to any location. Okay, so when we say that we need 20 or 25, we need 20 or 25 experimental units. So the experimental unit is defined as the smallest fraction of the experimental material where you can change the treatment. So if you inject your treatment to the animals, then you may decide each animal which is the treatment that you will will receive. But so the experimental unit here is the animal. But if, for instance, the treatment is given in the water and animals are in cages, are in pairs within the cage, then you cannot decide that one animal in the cage will have a treatment and the other animal will have a different treatment. So the treatment is given to the cage and the experimental unit is the cage. So but you will have two measurements, one from each one of the two animals. So the correct way of treating you have to simplify the measurements within the cage to a single measurement that applies to the cage, and the way to simplify, sometimes it is normally it is related to some kind of computing a mean. It can be just the algebraic mean, so the standard mean, or it can be a geometric mean or an harmonic mean, but you have to combine somehow those information to just a single number, and there must be some physical reasoning behind it. So the standard mean typically applies to most occasions, but you have to be careful and watch out in your domain what is the appropriate kind of computing averages. And so this is the situation. So let's say that we have treatments that can be applied to different animals. So there, for instance, we injected the treatment, and then from each one of the animals we can extract 3 aliquots or of whatever we are measuring. So we will have 3 numbers that are extracted from each one of the biological replicates. So this is the same situation as in here. So we have an experimental unit that in this latter case it is the animal. Then we have multiple measurements for each one of the experimental units, so we have to average them. So from the first animal, so this is animal 1, we will have 3 measurements that are indexed by I. So we compute the average of the 3, and for the second and the third animals we also do the same. So we compute the average of each one of them. And in this collection of numbers that we have here from the technical replicates, we will have 2 components. One is the variability between animals. So this is called the biological variance. So it is the variability simply because not all individuals respond in the same way. So let us refer to it as sigma squared b. So this is the variance, the biological variance. But then let's say that an animal has responded in some specific way, so just one number, let's say, but you are measuring that number through your aliquots, and then because not all regions in the animal will respond exactly with the same strength, or because you have noise in your analytical procedure, you will have 3 estimates of that number, that average number of the animal, and then these 3 numbers, they will not be the same, exactly the same. So they will also have some associated variance. I have called this sigma squared n for noise. So the variability, the total variability that you observe is the addition of the two. So it is the biological variance plus the noise variance. But because we are computing the average of these three technical replicates, actually the variance of the average is not the variance of each one of the test tubes individually. So the variance of the average is the biological variance plus the noise variance is divided by 3. So actually this shows that the variability of your measurements applied to the experimental unit, you can have a little bit of control on it. So this is something that we intuitively know, that if you measure multiple times and you compute the average, you have less variable observations. So you are dividing the noise by the number of technical replicates that you have. And this is important because when you compute the sample size, the variance that you need to use is the variance of your observations. So if you don't do technical replicates, they will be more noisy. Sometimes that's fine, and some other times by averaging you are gaining a lot. So it depends on what is actually the noise with respect to the biological variance. So if this term is much more important than this, then doing technical replicates more important in the sense that it is larger than this. So then doing biological technical replicates will decrease the will have an important impact on the variance of your observations. If this term is much smaller than this, then there is no point in making technical replicates. And another important source of variance might be given by some other variables. So let's say that in your experiment, sex and age of the animals or your patients or whatever can make a big difference. So maybe young males respond differently from old males or young females. So the point is that if you stratify your total sample according to these two other variables that you think that might make a difference, later in the analysis you will discover if they really make a difference or not. But the first thing is that at the experiment design you have to separate them, because otherwise you will not be able to analyze their contribution. So you divide your animals into the different subgroups. So for instance, here we make an homogeneous group of young males, here old males, and so on. And then at this point, once you have all the homogeneous groups, you randomize to the treatment groups. So you will have, for instance, in this slide, we have a new treatment compared to the current treatment. So 180, so a half of these animals will go to the new treatment, the other half will go to the current treatment, and this allocation has to be random. So an important feature here is that ideally it is better if the groups are balanced, but this is not a compulsory constraint. So if the groups are not balanced, still you will be able to analyze the data. So balancing has an implication on how easy is to analyze the data and to extract the different parameters of the different. So what is the contribution of sex, what is the contribution of age, what is the contribution of treatment. So it has an impact in that. It also has an impact in which comparisons are more or less noisy, but still the data can be analyzed. So that means that the unbalance means that you don't need 500 males and 500 females, and you don't need the same number of young and old animals all over the place. So in these blocks can be unbalanced, but you see that the treatment is balanced actually by randomizing at this level the number of animals in the treatment, in the new treatment and in the current treatment, they are the same. So that means that this factor is balanced. These two factors are not balanced. So this is very useful also. The thing is that why this is important, because when you want to show that the treatment is effective, you will have to show that the effect of the treatment is larger than the level of noise, so than the level of fluctuations that you see in your measurements. So and part of the fluctuations is caused, if part of the fluctuations are caused by sex and age, then you will be able to take away all these fluctuations caused by these two factors, and then you will compare your treatment only to the remaining part that you are unable to explain. And this noise here, this measurement noise, is part of the unexplained variance, and the biological variability that you are not able to explain, again, it is part of the unexplained variance. But if you are able to explain part of this biological replicate in terms of factors that you can measure, like sex and age, then those two components of the variability will be taken away from the comparison. So at the end, your experiment design should look like this. So you have all samples, then you make homogeneous groups. So in our example, we were doing young males, old males, young females, old females. And then at this point, we made a randomization. So there should be the concept of blocks, so homogeneous blocks in terms of some factors. And then once you have the homogeneous blocks, you have to randomize them. So this construction of blocks and randomization, it is what is called experimental design. So here you have an example of how this looks like. So let's say that you have three possible sources of variation in this experiment. So we not only have sex and age, but we also have two kinds of tumors. So you have to make homogeneous groups in terms of these three factors. So you would have old females with tumor 1, old females with tumor 2, young females with tumor 1, and so on. I'm not showing the full list. And then once you have an homogeneous block, now you randomize to the treatments. So these treatments here, in this example, I have a couple of treatment factors. So one is the treatment itself, that is A, B, C, and then these treatments can be given with an adjuvant or without the adjuvant. So you have here all kind of combinations, and it is important. So as we said before, it is not necessary that treatments are balanced. So it is not necessary that you have the same number of A's in each one of A's, B's, and C's within each group. So here we have 2 A's but 4 B's and only 1 C, and here we have only 1 A, 2 B's and 2 C's, and so on. But it is important that all of the treatments appear, so they don't need to be balanced, but somehow all blocks should see all treatments. If not all blocks are seeing all treatments, then still there are two possibilities. One is catastrophic, the other one is not. So the catastrophic one, at the end, it is the design is said to be you cannot analyze it because you will be confounding blocks with treatments, so you don't know what is the contribution of each one. And if it is not catastrophic, still it can be affected by it is said to be incomplete, and it can be affected, these comparisons, pair of comparisons between when you are comparing treatment A with treatment C, for instance, and C has not been seen in this block, then it is a little bit compromised, and especially the variances can be pretty large. So it is better if all treatments appear in all blocks. But if it doesn't happen, be aware that it can be catastrophic. Okay, let's look at this design. So let's say that you have calculated your N. So you have decided that you need 20 animals in treated animals and 20 controls, and you will have also 20 females and 20 males. And the experiment is such that it takes quite a lot of time, so you can only process 4 animals per day. So you have in total 40 animals, so it will take 10 days. And you decide to organize them in this way. So if you organize them in this way, so first week you will treat all controls, and the second week you will treat all treatments, and all controls will be female, all treatments will be male. So this is not a good design, and you see why. So one of the blocks that is females, or the same for male, doesn't see all the treatments. So this is one of the examples where I was saying we are confounding the block with the treatment. So that means that if I see a difference between control and treatment, I'm not sure if that is because of the treatment or it is because of the sex. Maybe the treatment doesn't make any difference, but it is sex that makes a difference, and then that is causing the difference that I'm seeing. So this is not a good design. So now this looks much better. So now we have the same number. You have females that are control and treatment, and the same for males. So you have control and treatment males, and now if you count the number of treated males and females, and the same for controls, they are balanced, so that's better. So the blocks in terms of sex are now balanced, so that's good. But now if we pay attention, we see that there are days that we only have males, same here. There are days with only females, and there are days with only controls. So that seems that okay, or there are days with more treatments than controls. So that seems that this is not good. So let's say that we have in our facility we have people working in shifts. So there is a person who works on Mondays, Wednesdays, and Fridays, and another person works on Tuesdays and Thursdays, and they will apply they will make our experiment. So maybe because some of the days, like this one, it is all made of controls, maybe the person working on Mondays works differently from the person working on Tuesdays. So maybe the difference that I see between control and treatment, it is simply because this person on Mondays has more controls just by chance, by this random distribution that I have done. So again, if the day can be a difference, can make a difference, then I would be confounding the day with the control and treatment. So this is not a completely balanced. So it is better if we design it in this way. So now every day there is the same number of control and treatments. So you see that every day there are always two controls, two treatments. One of the controls is female, the other control is male. One of the treatments is female, the other treatment is male. So, and the same happens every day. So this is a much better design. And within the day, for instance, if there is a specific pattern, so we have blocked the day now. So now we will factor out the variability caused by the days. Also another reason to block days, it can be maybe weather affects our measurement, or humidity, or whatever. So if some days are drier than others, then these could affect our measurement. Also, if you look at a specific day, you see that the treatments and controls and males, females, they are randomized. So we don't study all females in the morning or males in the afternoon. So if there is a pattern changing along the day, we will, by this randomization, it will tend to average to 0. Okay, so in general, the mantra that you should have in your mind would be control what you can. So what you can control is this randomization between control and treatment. Block what you cannot. So you cannot change the sex of an animal, but you can block the sex, so that you make an homogeneous group, and then within that group you randomize to the control and treatment, and randomize the rest. So control what you can, block what you cannot, and randomize the rest. And randomization can be randomize the position in the shelf. So for instance, maybe cages that are closer to the ceiling, because they are closest to the light, animals respond differently. Or if they are closer to the door, or they are closer to a heat source, or this kind of things. And randomize the feeding order, randomize the treatment time, the treatment order. I know people that randomize the pipettes that they use within their experiment. They also randomize the person that applies the experiment. So you can be very creative about all kind of randomizations. So let's stop here, this one, and then we will continue in the next one with how to calculate the sample size, and how there are 5 variables that are related to each other, and that fixing 4 of them automatically reveals the last one, and the last one that you are interested at this moment is the number of samples.